Example 3, a manager oversees 12 employees. He must select 3 employees for a promotion. And how many ways can the 3 employees be chosen? So see how we're picking 3 out of 12? A group from a larger group. Does the order matter here? He's just going to promote them. He didn't say one of them's, assistant manager or anything like that. Okay, he didn't name any of the positions. We're just picking 3 out of 12. That's just a combination. 12 choose 3. It's 220. Part B says, in how many ways can 3 employees be chosen for the positions of assistant manager, assistant to the assistant manager, and dishwasher? Now those 3 out of 12, the order matters because, you'd rather be the assistant manager maybe than the assistant to the assistant manager. You might have a preference. So the order matters. Now this becomes a permutation. Okay. Remember, a permutation is part of a factorial. That would be 12 times 11 times 10. But I think it's probably still easier just to type in 12p3. 12p3 is 1320. So pay attention to group from a larger group and whether or not order matters. That will tell you if it's a combination or a permutation. Number 4, you'll have a lot of problems that are talking about a deck of cards, okay? So make sure you know how many cards are in a deck, 52. How many cards are in each suit, 13. How many suits there are, 4. How many of each individual card, how many face cards and all that. Make sure you know stuff about cards for these type of questions. 5 cards are dealt from a standard 52 card deck. How many such hands have only face cards? Okay. Well, do you know how many face cards there are? There are 12 face cards, right? King, queen, and jack of each of the 4 suits. There are 12 face cards, and I'm selecting a group out of those 12. I'm selecting 5 of those cards out of 12, so it's a group from a group. Does the order that you get those cards in your hand matter? Doesn't matter if you have a king first and then a queen or vice versa. Order does not matter, so that's a combination. 12C5. 792. How many such hands have a full house of aces and 8s? Okay, so a full house means 3 cards of one kind and 2 cards of another kind. All right, this one specifically tells you exactly what it has. It has 3 aces and 2 8s. Okay, so I see the word and. So most of the time when you see the word and, you're going to treat it as a multiplication principle. Okay. I want to think about, here, I'll put it over here. I want to think about how many ways to get those aces. So think about it like this. Think about how many out of how many. Okay. How many aces are there? And how many am I selecting? How many aces are there? 4. And how many do I want? 3. Okay, so we're going to do 4, choose 3. Now we look at the 8s. How many 8s are there and how many am I selecting? 4, choose 2. We have 4, choose 3 times 4, choose 2. 4, choose 3 is 4. 4, choose 2 is 6. 4 times 6 is 24. That's a pretty good idea of what you're going to see. Some of the problems get kind of tough. They'll get tougher than that. How many such hands, meaning 5 cards, have exactly 2 hearts? Okay. People who are good at this are going to break this down and figure out what this means. Okay. Exactly 2 hearts has an implication. And that implication is 2 hearts and something else. You're holding in your hand 5 cards, 2 hearts, and 3 others, 3 non-hearts, if you will. Okay, so 3 others or 3 non-hearts. I like to rewrite the problem using the word and because it makes it obvious that it's going to be a multiplication principle problem. 2 hearts and 3 others. So think about the hearts, okay? How many hearts are there? 13, and I'm selecting 2 of them, and I don't care about the order. So then you think about the other cards, the non-hearts. How many cards are not hearts? 39, very good. That's a hard one. There are 39 other cards, and I'm selecting 3 of those other cards. Okay. So 13 choose 2. And 39 choose 3. 78 times 9,139. $712,842. Tough stuff there. How many such hands have cards of a single suit? Cards of a single suit. Okay. Now again, you want to really think about what that means. Okay. What that means is 5 hearts or 5 diamonds or 5 spades. That's supposed to be a spade. Or 5 clubs. See the word or? See how I put that word or in there? Or means plus. Okay? Or means plus. So I can go this plus this plus this plus this. We already did 5 hearts, didn't we? Or did we? No, I don't think we did. Never mind. How many cards, how many ways to deal 5 hearts out of 13? Well, that's just 13 choose 5. 13 hearts, I want 5 of them. Or 13 diamonds, I want 5 of them. Or 13 spades, I want 5 of them. Or 13 clubs, I want 5 of them. 13 choose 5. It's 1287. So if you're smart, you're probably just going to take your 1287 times 4, right? Times 4. 1287 times 4 is 5148. Ways of doing that. Remember, we are counting. Counting means find the number of ways of doing something. I'm not literally going to count all of those possibilities out. I'm not counting this and this and this all the way to 5,148. That's why I'm using these techniques, these formulas, these combinations. Okay, now, what you could have done, if you're really good at this, you're not going to do it exactly this way. You're going to say there are 4 suits, hearts, diamonds, spades, and clubs, and I'm going to choose one of those. And then once I've chosen one of the suits, then I know there are 13 cards in that suit, and I'm going to choose 5 of them. And what that's going to do is say 4 times 1287. So if you're really good at that problem, you'll do it this way. But I think it's a lot more clear if you call it 5 hearts or 5 diamonds or 5 spades or 5 clubs. So either way. Last one. Suppose 2 cans of soup are to be selected from 4 cans on a shelf. You've got noodle, bean, mushroom, and tomato. Illustrate the difference between permutations and combinations by making 2 tree diagrams of these soups. So notice we're taking 2 cans of soup out of the 4 different types. Okay, so basically we're trying to show the difference between 4P2 and 4C2. Okay, 4P2 we can do in our head. 4 times 3 is 12. 4C2 is a little bit harder to do. The formula is a little bit harder. So here was 4P2. Here's 4C2 is 6. Okay, so it says make a tree diagram. Don't have a whole lot of space here, so let's see what we can do. You've got noodle, bean, mushroom, tomato. That's my first can, my first choice. Okay. If order matters, then think about after your first can, noodle, you could choose the second one as bean or mushroom or tomato. And then if you choose the first one, bean, then your second choice could either be noodle, mushroom, or tomato. And then if you chose mushroom first, you could choose noodle or bean or tomato. And then if you chose tomato first, you could choose noodle, bean, or mushroom. Okay, so if you notice, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 leaves show the 12 different possibilities for that permutation, if order matters. Okay, so now let's think about if order does not matter. You'd still have your first choices the same: noodle, bean, mushroom, and tomato, but this one's going to be a little bit different. Okay, your first can was noodle, then your second choice would be bean, mushroom, or tomato. But then after that, it gets a little bit different because if your first choice was bean, then you wouldn't do the noodle branch because bean noodle is the same thing as noodle bean. If order doesn't matter, then bean first, noodle second is the same thing as noodle first, bean second. So I'm not going to do bean noodle. I'll just go straight to bean mushroom or bean tomato. Likewise, when you start with mushroom, you've already got NM and BM. So all you'd have is what? All you'd have is mushroom tomato left if order doesn't matter. Okay. And so once you get to T, you've already got everything with T. You've got noodle tomato, you got bean tomato, you got mushroom tomato. That's it. That's the only possibilities. So there's really only 1, 2, 3, 4, 5, 6 possible ways of doing it if order doesn't matter. So there's your combination.